Do we need to share this on Zoom also, probably? Can we open something, please? Because it's very hard to breathe. Yeah. Maybe that will be enough. This thing also, I think, opens. Yeah, there's no need to freeze flow though. We can open this door.
I don't mind.
I don't mind freezing.
Okay, so with apologies for the delay, Alexei Grinbaum, it's very wonderful to have you here to give your talk on, as I understand it, the quantum information and the quest for reconstruction.
Thank you, Simon. That's exactly the talk I'm not going to give. So, yes, so my area is quantum information and the variant of quantum information and quantum foundations, and we can talk about reconstructions, axiomatic reconstructions, more modern topics like causal orders, like contextuality, various non-classical resources, and the varying on quantum foundations. All of that cannot be really seriously done in 20 minutes. So I've chosen instead to do a very, very small 20-minute talk telling you about the new version of John Wheeler's 20 questions game, and then trying to draw some lessons on that. So if you're not familiar with the game, that's the game. That hasn't been planned, but we're probably very interesting. Oh, okay. Thank you for for the melody. So the game suggested by Wheeler Inventors is a variation on an old American TV game, and Wheeler's variation goes like this. There are players in the room who do not agree to choose any word in advance. Because in the original game, they agreed to choose a word when one player was out of the room. Now, there are players in the room, they don't choose any word, then the main guy comes in, and starts asking binary questions. Does it have legs? Somebody says yes or no. Can it fly? Somebody else says yes or no. And so on and so forth. People take more and more time to answer the question, and at the end, after 18 or 19 questions, the main player says, well, it should be a cloud. And everybody starts congratulating everybody because John Wheeler said they had not chosen a concept before, so every player had to come up with a word compatible with all previous answers and give their own answer. And that's how it happens in quantum mechanics, says John Wheeler. The system doesn't pre-exist out there. It comes as a sequence of yes-no questions, and here's, I think, a new point. What if that sequence doesn't converge? Can we say that these questions are about something? What if, in the end, there's no winning moment? There's no moment when the main player says it's a cloud. Can we say that there is still some information that comes out of these inputs and outputs? And I think that yes. I think that what is happening in quantum information in the last 25 years is that we're learning that this information is not about that unknown term, cloud. It doesn't have a semantic, and that's one of the main lessons in several publications, including this chapter here in this volume. I've been trying to argue about that. So the most simple and really paradigmatic example are Popescu-Rowley boxes. So let me remind you that Popescu-Rowley boxes are non-signaling boxes introduced in 1993, 1994 by Sandra Popescu and Daniel Rowley. Are non-signaling boxes introduced with the question of seeing whether non-signaling led us directly to the Zilson bound. And the surprising answer was that it did not. So if we only focus on inputs and outputs in the box, and on the joint probability distribution of the outputs given the inputs, then we can actually imagine a model that gives us correlations that are stronger than quantum correlations. And as most of you, I guess, know, these bounds, the classical bound and the maximal non-local bound, are polytopes, and the quantum bound here is not a polytope. It's actually not a computable bound. So that model, which is now 30 years old, has given rise to a whole tradition of various box models, and I'm not going to talk about others. It's a part also, as I see it at least, of what can be called device-independent approaches. Device-independent approaches meaning that we don't know or we don't trust for some reason that inside the box there are, let's say, photons or such and such systems, but we still want to do physics without presuming any knowledge of what exactly lives inside that box, what is doing the physical job. So we can still do it, as we can do it with PR boxes, without knowing what's in the box. We can talk about computing stage to stage. We can talk about doing communication with these models. We can talk about properties of these maximally non-local worlds. And of course, we can talk about the Zerolson bound seen from the point of view of this new paradigm of quantum theory, where the Zerolson bound is just one strange number somewhere in the middle between 2 and 4. And the question becomes, why is it the Zerolson bound and not something else? So before addressing the history of reconstructions, which I will do in a second, I was trying 5 years ago, and also in this chapter, to sort of really cash out on the philosophical lessons rather than mathematical lessons of what is going on. And I think it is a new and quite a radical shift in the philosophy of quantum mechanics as to speak about these physical processes that are of unspecified character or of unknown nature. We don't know what's in there, but we can still do physics. So of course, when I say it's quite radical and quite new, probably most of you in this room think, oh, no. Of course there are historical parallels. And I'm going to give you some, indeed. But I do think that one of the crucial lessons of the last 25 years in quantum foundations, and this comes from research in things like indefinite causal orders, almost quantum correlations, and many other topics, on quantum contextuality, generalized contextuality, and so forth, that one of those main lessons is that assuming that you have a cloud or a system in your box, that you have it somewhere, is not a given. So in John Wheeler's game, if the answers diverge, it doesn't mean that the game has been lost. It means maybe that the initial presupposition that people have chosen one word was the wrong one. Maybe something else was going on, and we just didn't get it correctly. Maybe they had chosen 2 words, maybe they had chosen n words, we don't know. But so the idea that there is a system to start with should be put into question. Now, of course, this is kind of similar to Einstein being unhappy with principal theories and claiming that there should be constructive theories. So you remember this from the 1919 Times article by Einstein. He wanted to replace principal theories with constructive theories, except that that never came about. We're more than 100 years later. Now we believe that principal theories are as good physical theories as constructive theories. So what if knowledge of specification of the system never came? I think what we're learning from things like indefinite causal orders and quantum information is that those theories can very well be good physical theories. We don't have to say that there should be systems. Now, very quickly, maybe two flashbacks into history to support this argument. So now I've given you the gist of the main argument I've been trying to defend in various papers. Now, this comes first from the long tradition of reconstructions of quantum theory. Axiomatic reconstructions, as you know, started with von Neumann and Virchow in 1935. In the last 30 or so years, information theoretic reconstructions have taken that place. And in the business of information theoretic reconstructions, we've learned that there are two key postulates that make things quantum. One is the amount of correlations, the ones I just mentioned. Why the Thorsen bound? Why not slightly more? Why not all the way to 4, to maximal CHSH? Why not slightly less? Like, what is it? What principle drives us exactly into 2 square root of 2 and not something else? And they're having, of course, the best known example is information causality from Marcin Pawlowski and company in 2009. There are several other examples. We still don't have a very good understanding of this, but we have now a theorem that says that whatever bipartite principle you have, so whatever principle you may want to have about Alice and Bob, it's not enough. Any kind of bipartite principle will not give you quantum theory fully. It will give you 15/16ths of quantum theory. We can even quantify how much. But not, so we know that there's something in quantum theory, in quantum correlations, that escapes from this bipartite view. Another element that needs to be brought into your system of axioms in order to get quantum mechanics is continuity. One is the amount of correlations and the other one is continuity. Actually, if you have a probabilistic model with these two axioms, you will have quantum theory. Continuity can be formulated precisely in different ways. You can talk about continuous transformations between pure states on the sphere. You can talk about, as Nicolas Jussin, for example, does in his recent work, about the necessity for complex numbers and not some other number field. So you can have various phases and various versions of continuity axiom. In the end, this will be something about continuity. If you have a discrete field, or if you have a non-number field, let's say a polynomial field, behind your Hilbert space, on which you build a Hilbert space, you will not have quantum theory. So these two axioms make things quantum. And I think we've learned it in the last 25 years. We've learned it thanks to all these information theoretic approaches. And now we're trying to play with these axioms. Of course, we're trying to say, well, okay, what happens if we don't have one or another, if we replace it? So there is a lot of game going on. There are a lot of different versions and models going on. And one of those, just quickly, the one I've been also interested in for the last 10, even more than 10 years now, are indefinite causal orders. Now, very quickly, if you haven't heard about indefinite causal orders, the idea is to put the Alice's lab and Bob's lab not in a defined temporal order. One is before the other, but in a superposition, in an order which is like a Schrödinger cat, in a superposition of orders. And this can be done in several mathematical frameworks. One is called the quantum switch, another one is called process matrices, yet another one is called supermaps. There are other approaches. Now this has become quite a big science area, discipline within quantum information. What is very interesting in these causal orders are the attempts to make experiments. Of course, scientifically and theoretically they're also very interesting, but because I have limited time, let me just tell you one thing about these causal orders. When we try to make experiments in which Alice and Bob are not one before the other, but there is a control, a quantum control that puts them in a superposition of orders. People say, no, 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 you haven't really done the experiment right. You've simulated an indefinite causal order, but this is not a true indefinite causal order. Why is that? Because quantum control and the target degrees of freedom are actually degrees of freedom of the same system, because we don't know how to separate them. But the lesson from this is that all these strange situations allowed by the Hilbert space are very difficult, of course, to realize empirically, to build experimentally. Not so much because the mathematics is difficult or whatever, the mathematics is not very difficult, but because when we're building things, we, of course, come with this idea that there's a source and there is a detector. Whereas quantum information in these abstract Hilbert spaces shows us that there are resources that are non-classical, that are quantum resources, like the indefinite causal order, that cannot be easily fleshed out in terms of a system coming out of a source and going into a detector. That's just not the appropriate language for working with these resources. So we have today situations like also generalized contextuality situations, something called the Lugano process, so I'm not defining these things. There are plenty of things on the market, which are not easy to define in the language of quantum systems coming out of sources and going into the detectors. So we start to learn that maybe that assumption also needs to be shifted to, or shifted to the second order level. So to conclude, we have this, and Tom Reichman will speak right after me, we have the discussion with Tom whether Einstein always put quotation marks around real or not. And there is a letter found by Don Howard, I think, a letter to Schrödinger in 1935 where Einstein clearly says, I want psi to be about the real state of the real system. Although later, and Tom will show you, I guess, this, later he always put real in quotation marks. So when he was really careful. And this is the EPR argument. But this is an old mode of thinking about systems. For me, what is really interesting here is this. The word real, of course, is subject to the debate about entity realism, property realism, all those kinds of realism. But the very word system maybe has to go. So look at this. This is from Bob Kuke from also some time ago. So here you will see that systems are a kind of derivative notion. We have these symbolic diagrams that describe information flow, or we can talk about ZX diagrams, we can talk about circuits, we can talk about all sorts of diagrammatic languages, and systems are really those stuff that lives on the wires. But we don't have to start with that. So this does introduce, I think, a paradigm shift that is quite interesting and radical and comes from all this research on causal orders, almost quantum correlations, and so on and so forth. So to end with Wheeler, again, I started with the game of 20 questions, and in your reading, let me end with Wheeler, and I really admire Wheeler, who was a fantastic visionary. When Wheeler said this in the early 70s, I don't think many people understood very well what he was talking about. I think today we're in a much better position to understand this. The propositions, meaning these binary propositions, are not propositions about anything. So when people say, oh, you talk about quantum information, what is information about? No, it's not about anything. That's a meaningless question. They are the abstract building blocks. Well, Wheeler said in his time, pre-geometry, out of which reality, quote unquote, you see the Einsteinian quotation marks, is conceived. So this aboutness or semantics of information, I think, needs to go, and with that, the very notion of system that is somehow predefined, presupposed, needs to go. And that's what, this is for me, one of the interesting lessons of the last 25 years of quantum information. Thank you. So the mathematics here is the mathematics of...
Because you give quotation, but it is not understandable which was next to bring it.
Okay, so let's take one example. As I said, in indefinite causal orders, there are different mathematical frameworks in which you can define what you mean by an indefinite causal order. One of them is called supermaps. So supermaps are, or process matrices, that's really the same thing. They use the Choi-Hamilkovsky isomorphism between, I'm going to use a lot of mathematical words, right? So, sorry. So, when you talk about maps between input and output spaces, so here myself all the time. So, for Alice, this is the input and the output space. This is for Bob, the input and the output space. So here they are. Maps from these on those can correspond by Choi-Hamilkovsky isomorphism to states. There are, of course, positive and all that positive normalized states on this high-dimensional Hilbert space. So this is algebraic. This is an algebraic approach, if you like. There's no dynamics. We're talking about algebraic properties of Hilbert spaces, as we do often in quantum information. So these are Hilbert spaces. We can do different things when we talk about what is called GPTs. So this is a GPT. This is a generalized probabilistic theory, GPT, meaning that this theory is given, can be given in a Jordan algebra. It can be given in a very formal way also as a set of these probabilities. If you want rigorous mathematics, you have to go to Jordan algebras or effect algebras, as they are called also by different schools of mathematical physics. So these are more general than quantum. And in that case, you can talk in those mathematical frameworks. You can talk about these generalized theories. So these are probabilistic models with rigorous mathematics, but they are not quantum. So this is not a von Neumann algebra, this is not a C-star algebra, this is an effect of Jordan algebra, a more general kind of beast. And in that case, you can ask the question, what are the conditions that drive me back into quantum? For other various axiomatics, you can do various other mathematical frameworks. So typically, these sets of axioms come as simple physical principles, let's say something about probabilities, something about correlations, something about continuity, and then you translate them into a mathematical language. And these mathematical languages are not uniquely defined. You can talk about algebraic models in the language of algebras. You can talk about probabilistic models just in the language of convex spaces. If you're already quantum, you can live in a Hilbert space, but in a high-dimensional Hilbert space. So this mathematics is not very difficult, but it contains, to finish up, it contains a lot of interesting, not even topology, but homology. So one of the ways to think about things like generalized contextuality is to use algebraic topology and cohomologies on these vector spaces. So then we will have quite advanced classifications.
Okay.
Yeah. Thanks for the talk. I have a question about kind of the overall conclusion. So I really like your emphasis on principal theories as legitimate theories, right? But I'm not sure that that's enough to go from the propositions are not about anything. Like maybe you could say like, look, thermodynamics is a good principal theory. It's about gases and whatnot, right? Heat and things like that. Why go the further step and say this is not just principles, but they are not principles about something?
Yes.
Why the further?
Thanks. Yeah, that's exactly because in the 15-minute talk I've jumped across the full contents that I needed to develop, right? So there's a paper in Studies in 2017, and also this chapter, both of them develop this argument in detail. You're right that if you take any particular axiomatic approach, it's not clear why. But what I'm trying to do in those papers is if you bring together different lessons from these different axiomatic approaches, plus this relatively new research on things like causal orders, on things like contextuality, and so on and so forth, then from bring you all these things together, you start seeing some, unusual conclusions. But definitely, I haven't developed the details of the argument here. Yes, sorry about that.
This consideration about input and outputs plans to be formalized in the game theoretic degree theory of Christophe Chalon.
Okay.
If you want, I can send
Sure, send me an email.
his PhD.
Yeah.
Okay.
Yeah, so one of the questions, just to answer this quickly, I don't know that game. One of the interesting questions right now in quantum foundations is how much work does the input-output distinction do? Can we get rid of that distinction between types of data and still do some physically interesting work? Or do we have to have it, or if we have it, how far are things determined already just by this distinction? So if you have a string of zeros and ones, you say, this is a string of inputs, this is a string of outputs. What can you do? Can you compute correlations already? So a lot of work goes on this very high level of abstraction today.
Okay, I think that we'll thank our speaker now.